The question is, can we do this effectively, all this simulation? One of the problem is whether can we automatize this process. So can we create some generator of the samples for our input parameters, which then conduct the simulation, sum up the results and calculate risk for us. So in other words, we need some generator of the sample, which prepared for us input parameters. But the more interesting question is, can we do this more effectively? So do we really need to calculate or run the simulation for each of the possible fire scenario to get the good estimate of the risk behind this building and behind these scenarios? Is there any method which we can use that is able to calculate risk on the limited number of the samples? There are such methods, and one of them is the Monte Carlo method or Monte Carlo simulation. The method is credited to Stanisław Ulam. He was a Polish-American mathematician, and the history of the Monte Carlo method is quite interesting, and I'm going to bring you very shortly. Stanisław Ulam had very serious brain surgery, and he recovered in hospital after this surgery. The hospital is not very interesting place, and Stanisław Ulam was bored during the stay in this hospital. And in order to spend the time more effectively, he started to play in a solitaire. And after future trials as a mathematician, he tried to evaluate the probability, the success of the solitaire. Yes, and he tried to solve this problem using the analytical method, so try to find some equation or some iterative method and so on and so forth in order to evaluate the probability that the success in the solitaire. But he failed. After the long consideration, he realized that the only way to calculate the probability that the success in solitaire will be playing all the possible, games. So all the possible configuration of the cards, and then calculate the number when they are finished with success to the total number of all these combination, and then this will be estimate or the result of the probability that the success in solitaire. And he started to play solitaire, and after, let's say, a number of trials, he realized that he is able to evaluate the probability very efficiently. He observed that the probability start to converge to some set value, to some defined value. So even if he was far from the playing all the possible combination, he obtained a very good estimation of the probability, and they stay on the same level with low fluctuation. And in this way, the Monte Carlo method was born, and the Monte Carlo method is just the method of evaluating the population mean based on the sample gathered from this simulation, from this population. And so this is it can be used for the estimation of the mean value, but also for the integration of integration problem And the main idea is just to draw a random parameter, then calculate the function which we use, obtain the output parameter, and then calculate the probabilities of given output parameters, mean or probabilities that some value will be achieved. The mathematical formulation of the Monte Carlo method. The Monte Carlo method has been already discussed in one of the previous lectures. However, now we are going to bring some key formulas and key definition of this method. So the goal of Monte Carlo method is to estimate population expectation by the corresponding sample expectation. So let us define an expected value of some random variable y. The mean of this expected value is defined as follows. So the formula 3. In order to evaluate the expected value, we generate some values from this distribution. These values should be independently and randomly chosen from the discrete distribution y. And then we take their average of this expectation. And then, if we take an average from our sample size, we obtain the estimation of the population expectation. Yeah? In this case, we have the approximation of the population expectation based on the sample size n. And this is the core idea of the Monte Carlo simulation. So take some sample size from the distribution and then try to evaluate on the basis of these samples the expected value or the mean value which we are going to use. The Monte Carlo method is also used for integration, but we are not going to discuss this now because it is not used in our approach. The key question is how good is our estimation with this? So try to calculate the error related to this estimation. So we have the population expectation, and we have also our approximation based on the sample size n, and the expected value of these errors can be calculated as follows. This is also the variance related to this error. So the variance of this error is directly proportional to the square root of the standard deviation, or to the variance of the population divided by the sample size. So the bigger the sample size, the lower the error of the approximation. Okay, so the root mean square error can be calculated as follows, and it equals the standard deviation of the population divided by the square root of sample size. So the standard deviation of the population, we may say that is constant, yes, because this is the some feature of the population. So we can decrease the root mean square errors by increasing the sample size. And therefore the convergence rate of the Monte Carlo is of the order of square root to the n. And so this is the convergent rate. Okay, but still we have the approximation of the root mean square error of our approximation, but we need the standard deviation of the population, which is in normal cases unknown, but in our problem, in most cases, we are interested in good estimation of expected value rather than good estimation of the error. So we can also use the expectation of the standard deviation or the variance of the population from the sample size. So instead of calculating or trying to calculate the population variance, we can also approximate this variance based on our sample. And here we have the formula for the approximation of the variance of the population. And then, because the Monte Carlo is unbiased, you have already discussed this, so we can calculate, we are able to calculate the confidence interval for our approximation. So here we have our approximated value taken from the sample, and then the error is related to the standard normal deviation at some, let's say, alpha value, if we would like, times to the standard deviation approximated from the sample, divided by the square root of n. So if you would like to have 0.95 confidence value, we should use the following formula. So this is our expected value, so approximation of the expected value of the population mean, and the error is in the range 1.96 times the approximated this way the standard deviation divided by the sample size. We discussed so far the calculation of the approximation of mean value of the of some distribution or some random variable and the error related to this approximation. But in the case of the Monte Carlo simulation, in the case of risk assessment, in most cases we are interested in estimating the probabilities. For example, the probability that somebody dies in fire, the probability that some critical value of temperature will be achieved, and so on and so forth. So this is also possible with using Monte Carlo simulations. So let's say that we have some approximation. Here we have some distribution of random variable temperature, which is the output from our simulations. Yes. So we have some, let's say, mean value of this and standard deviation of this distribution. However, we are interested in probability that the temperature will be higher than 300 degrees of Celsius. Yes. In order to evaluate this probability, we have to define some indicator function, and this function is very simple. Just return 1 if the x, our x value, are in some set A. Our set A can be defined as a temperature greater than 300 degrees of Celsius, and 0 otherwise. Yeah? So, for example, in this, when our value taken is in the range from lower than this defined value. So, and once again, the probability can be calculated as follows. This is also the mean value of this indicator function. So in this place, and also the confidence interval. So how good are our estimation of this probability? So once again, this is this probability we calculate, and taken from the standard normal distribution for the 0.95 confidence interval. Yes, and again we should back here, so we have the standard deviation or variance divided by the sample size. So the variance of this of the distribution, this is the Bernoulli distribution, can be calculated as follows. So the probability of our event, for example, that the temperature will be achieved, times the 1 minus this probability. This is the variance. And here we have the sample size. So the error related to our approximation of probabilities can be defined as follows. The other type of problem which we face during the Monte Carlo simulation or risk assessment is the estimation of the quantile. As exemplary problem, I serve the problem of finding the cutoff value for the temperature. Here we have the distribution of this temperature, for which the probability of such value or lower equals 95%. Yes, so we are interested that some cutoff value, t, where the value greater than this t value has the probability 5%. Yeah, so this is the definition of the quantile estimation problem. So the estimation of the quantile is an inverse problem of the estimation of the probability. And such a probability can be estimated using cumulative distribution function. And therefore, the quantile function is sometimes called the inverse cumulative distribution function. So here we have the quantile function with some probability p, in this case 0.95 this p is in our problem, and this is the inverse cumulative distribution function and can be defined as follows. So we are going to find the x from R, which p of this value is lower than this cumulative distribution function. This is the inverse function. So in order to find this quantile, so we are going also to use the Monte Carlo simulation. So we generate some sample size n, and then in order to find the quantile with some probability, let's say p, we should sort this value ascending from the lowest to the highest value. This is the n value, and then choose the n times p sample from our set, from our ordered set. So, for example, we would like to calculate the cutoff value, the t value, which is 0.95. Yes, that the value greater than this value is probability less than 5%. Let us assume that we generate 10,000 sample size. Yeah? So we should choose the value, n is the 0.95 times 10,000. So we should take the value from this set 9,500, and let's say that this value is 312 Celsius of degree. So in this way we calculate the quantiles. We also interested in calculation of the error related to our estimation, and because now this calculation of the quantile is biased, we cannot use the method which we used previously, and the calculation of the confidence intervals is not very straightforward for the quantiles and the Monte Carlo approximations. There are some approaches, and the problem based on the difficulty of the problem is based on whether we have the parametric distribution or non-parametric distribution. So if we would like to, we are interested the other method, here we have the literature or the paper, the book, which we can then read it further. However, the general idea is provided here. So in order to evaluate the confidence interval for our quantile, we should choose integers L as a lower, yeah, and the upper, so we should some value lower than the upper, in such that L is greater than 0, U is greater than L, and the sample size is greater than N. And we have to solve such solutions. For example, here we have this confidence interval, and solving this equation, we should choose the value L and U which define as a confidence interval. So that is it regarding the mathematical formulation we use. And let's back to the general idea of the Monte Carlo simulation. So we have some sample generators. Yes, for example, we have some various input parameters for our fire models, and we draw these parameters from the distributions placed to the fire models, for example CFAS or FDS or other fire models, and then they perform the simulations, and we have some estimation of the output value regarding whether this is the continuous probability distribution. We might check the probability that some value is greater than some defined value, as in the case of the temperature, or the output can be discrete, and here we have, for example, the probability that somebody dies. So this is the general idea of the Monte Carlo simulation, and this idea is already known by you, so you use this in probabilistic fire simulator, in the estimation of the, let's say, the probability that some temperature which destroy the cable can be achieved. But now we are going to expand somehow this approach by adding more models and more input parameters. So let us now introduce the multi-simulation approach, which is somehow the expansion of the Monte Carlo based probabilistic risk assessment used, for example, in probabilistic fire simulator. The expansion is based that instead of one, let's say, models such as fire models, we have all the, let's say, or nearly all the models related to the fire, predicting the fire, or related to the fire phenomena. So we have some set of models. These include the evacuation model, fire models, also some constructions, reaction of the construction to the fire models, and other models which we can use to predict the output of the fire or the impact of the fire on the structure, on the property, or on the human. And so we have the set of the models. We have some fixed parameters, a set of fixed parameters Z. This is the vector of these parameters, and this parameter represent, for example, the geometry of the buildings, let's say the physical properties of the walls, and other parameters which that do not change during the simulation. And we also have this sample generator. So all the parameters which are uncertain, which are variate, can be drawn from the defined distributions. Yes, so we have some fixed parameter values, then the sample generator, and we have the set of models related to the predicting the fire phenomena, or the output value related to the fire. And as an output we have some values also in a form of probability distribution, which we are interested in. So the name of the multi-simulation is derived from the multi-models Monte Carlo simulations. And so if we think about the models related to the predicting fire phenomena, here is some example of such models. So of course the central role plays the fire models and the evacuation models. So as we discussed in previous slides, we have the joint fire and evacuation modeling, and also we can add other models to this joint modeling. And for example, the fire model produces the data related to the visibility, which affects the speed of the evacuees, or the smoke aware evacuation, which means that evacuees try to find the way free of smoke. So this is the core models. We have also some fire brigade intervention models, because the fire brigades affect the fire, so try to extinguish or remove the smoke from the building by the ventilation, and also affect evacuation. For example, they shorten the pre-evacuation time. And the data from the fire models goes to the evacuation and visibility models, and also for example, for the structure stability model, the model which try to predict let's say, whether the critical temperature is achieved in let's say, the construction of the steel elements, or even the mechanical response. And these models produce some data which can be further used for evaluating the consequences. And at a given time we have three types of consequences. So the traumatic injury related to the loss of the construction stability, and the position of the evacuees of the building related to the element that collapse. We have also toxic injury model based on the Purser FED equation, which we already discussed. And we have also thermal burn model, which based also on FED but related to the convective and radiative flux. So this type of models can be used, and these models are fed with the data from the Monte Carlo sampler. So this is the general idea. Take all the possible models related to the predicting the fires and phenomena, and prepare the sample generator to the parameters that are uncertain or variate, and generate the numbers of simulation and try to sum up data generated by this model and the simulation. And the multi-simulation approach, in order to use this approach, there is a special tool prepared. The tool is called AMX. AMX is the implementation of the multi-simulation approach. And here we have the main modules of the AMX. So first one is the GUI module, which allows us to draw the models of the building, to define the parameters of the building. Then we have the AGEO modules, which is responsible for preparing the input file for fire models, for evacuation model, for structural stability models, and other. Then we have module responsible for generating the samples for these simulations. We have also included the fire model, evacuation model, yes, and the evacuation and fire evacuation are the joint simulations. So fire can affect the, let's say, the simulation in the form of the decreasing the speed or in the direction of the evacuation, depending on the place when the fire is and the optical density of this fire. And therefore we performed a number of simulations. So we face the problem of performance. So we need, let's say, some hardware resources to make this simulation in acceptable time. So if we would like to run the 5,000 simulations, so we need the special infrastructure to do it efficiently. So we have some grid module, which is responsible for sharing job, for managing the workers, for gathering the data, and everything what is related to the grid architecture. So after the definition of this, the number of simulation, the grid module is responsible for giving the jobs to worker, so in the means of some nodes of this grid, and then collecting the data. And we also have some module for the visualization, so we can observe how these people evacuate, what are the problems with this building, and so on and so forth. And we have also modules responsible for result, so the probability distribution, the event tree, FN curve, and so on are generated by this model. And here we have the workflow of this AMX software. So we start from the GUI when we prepare the model of our building, or we prepare the candidate design, so some safety measure implemented with this building. We define the input parameter, the number of simulations, and so on. And then we have the geometry module, which is responsible for preparing geometry for fire and evacuation modules and other modules, because in most cases each of these modules has its own geometry. For example, comparing FDS and CFAS, each of these software has another type of input or definition of the geometry as an input file. And then we have the Monte Carlo sampler, so it generates the number of samples, the number of the simulation. This is the simulation, so which has defined the strict parameters. So we have the number of the input file for CFAS and for evacuation modules. So the simulation are discrete, so we have, for example, 1000 discrete simulation, and they are they go to the grid manager, which is responsible for performing this simulation. So grid has a number of nodes, computers, and it shares this job with this worker and collect the data and manage that all the jobs should be performed correctly. Of course, manage the errors and so on and so forth. So after the nodes or workers generate the number of simulation of the output data, the data are collected once again on the server and generate some chart, some visualization in a form of animation and various type of chart. And finally, so because the AMX is responsible for the calculation of the risk, but what is the topic of our next lecture, how to deal with calculated risk. So we have some cost-benefit analysis and the final decision whether the building is safe or not, or is approved or not. So this is the idea of AMX software, which is the implementation of multi-simulation. Let us now discuss how the risk for human is calculated in AMX software. So the probability of the various scenarios, we already know how this is calculated. It is just from the Monte Carlo simulation, the approximation of the probability. But how are the consequences for human are calculated? As we mentioned in one of the previous slides, the consequences of severity of for human from the contact with smoke are based on the fractional effective dose approach. And for example, for the toxical effect, we use the equation defined by Pursuer. So let's say agents or evacuees move in the fire environment because the evacuation of fire and because the simulation of fire and evacuation are joined, so evacuees are moving throughout the smoke if there is no other way. And the exposition, so exposition to the toxic gases are calculated. For each step we calculate the concentration of each of these toxic species and the time of the exposition, and we multiply this by the hyperventilation effect of high concentration of carbon dioxide and low concentration of oxygen. And when the simulation is finished, each of the evacuees displays some value of fat they gathered during the evacuation. And now we have to decide what are the severities, or what are the consequences of such value of fat. And in order to define the consequences, we use the log normal distribution function. And for example, for the fatality or lethality effect of the fat, we use this cumulative distribution function, which for the value of fat equals 1 achieve the probability that equals 0.5. So there is a 50% chance that with the fat value that equals 1, the given evacuee will be dead. So in this way. So at the end of the simulations, we obtain, depending on the fat, so we obtain the various probabilities of to be dead. Yes, for depending on the fat value, we obtain the probability that somebody will die in this fire. So we set for each of the evacuees, we set this value, and in order to calculate the individual risk, and individual risk can be explained that probability that at least one person or one evacuee dies. So having the vector of the probabilities that for each of the evacuees, we can calculate this algebraically, the probability that at least one person dies. So in this way we calculate the individual risk, so based on the severity. And for serious injured, we have also the same log normal distribution function. However, in this case, the 50% of chance is set on the 0.3 value of fat. So having the 0.3 value of fat, there is a 50% chance that the person will be seriously injured. So this is the model. And of course, first we start with, so each of the evacuees displays some value of fat. First we calculate the probability that somebody dies, yes, and then we calculate that is seriously injured. And then the probabilities that, so for each of the evacuees we calculate these two probabilities, and when there is a probability that individual risk that somebody dies, we have to then add, subtract this probability that the probability is seriously injured, because one person can be either dead or seriously injured. So in this way we calculate the individual risk. Yes, so the probability that at least one person die, or the probability that at least one person will be seriously injured. So this is the risk for human. However, for the societal risk, this is a little bit complicated, because we have to calculate not only the value that at least one person died, rather than we have to calculate values that that one and more person died, two and more person died, three and more person died, and so this is much more complicated. And therefore, in order to calculate the severity in the case of societal risk, we use the strict values on the ranges. And in the case when the fat gathered by human is greater than 1, this is the lethal effect. If it is in the range 0.3 to 1, it is heavy or seriously injured, so lingering health problems or permanent disability. And if it's in this range, this is light injured and low consequences, so short injured. And so based on this approach, we define the number of fatalities, the number of heavy injured and others, and based on this we create the FN curve. And the output data regarding the individual risk is presented in the form of event tree. So starting from the probability of the ignition of the fire, which is taken from the statistic, and we will discuss it later. So the probability of the ignition in the building, then the probability of early suppression. So these values are taken from the statistics, and here from this start the Monte Carlo simulations. So here, if there is no people that had contact with smoke, so in this case the scenario when the ASET has been longer than RSET. Yes, so there is some set of the scenario in our Monte Carlo simulation when there people hadn't contact with smoke. Yes, for those number of simulations, number of scenarios when they have contact with smoke, we calculate the Fed value, and based on the Fed value and the probability distribution I discussed in previous slide, we calculate the individual risk. So here we have, let's say, the probability that somebody dies in the fire. This is this branch. And here is the probability that the person had contact with smoke, but it wasn't at the lethal effect. Yes, so this is seriously injured, light injured, and seriously injured and light injured. Yes, and this should be expanded further in the other event trees. But if you would like to know the individual risk from this event tree, individual risks of death, we should use these probabilities. Okay, and some information about how the ignition, fire ignition probability is calculated. So we use generalized Barrois model, and here is a two exponential function with some coefficients C1, C2, and some exponents R and S. And each of these data are taken from this table. Once again, this is the data for the Finland, prepared by Kati Tilander. And here we have the type of the building, yes, and the parameters C1, C2, R, and S. A is the area of the building. So if you would like to calculate the risk of fire ignition, or the probability of fire ignition, probability of fire ignition for the educational building, so we should take these parameters for the educational building and place here, and we obtain the ignition probability in educational building. So this is our starting point here. The probability of early suppression is also taken from the statistic. The rest is calculated by Monte Carlo simulation. And also we calculate, as I mentioned, the societal risk. The societal risk is based on the complementary cumulative distribution function. So this is the definition. So CCDF, this function is also known as a survival function or survival analysis, a reliability function in engineering, or for short FN curves in risk analysis. And FN curve is two-dimensional relationship between frequency and the cumulative severity of outcome. Frequency, you know, and cumulative severity, so one and more people, two and more people, and so on. And here we have some example of FN curve. So the FN curves from the some simulation for fatalities, serious injuries and minor injuries. And here we have the very high probability, but this probability should be multiplied by the risk from here that at least one person die. So this is the risk that at least one person die, and here we have the manifestation, the number of persons, the function of frequency. How the FN curves are calculated, as I mentioned, it is based regarding the consequences on the sharp ranges, depending on the path. So the calculation of the FN curve is as follows. So we have the n scenarios or n Monte Carlo simulations. We have the frequency of each scenario, we have the consequences, and we start from the highest consequences. This is the highest consequence, F1 cumulative frequency, that there was probability that, let's say, 300 persons will die, and then we sum up the consequences regarding the scenario and sum up the frequency, and this is the cumulative frequency. Okay, so this is it regarding the theory, and now there is a time to try it out, to play with AMCs and calculate a risk for some simple building, just to make aware of the AMCs software.